In this screencast, we'll talk about inferential statistics for one population proportion. So first let's talk about the difference between a parameter and a statistic. A parameter is a number which describes the whole population. The population mean, mu, population standard deviation sigma, proportion p. And we usually can't measure this number directly because the population is too big. We couldn't find the mean weight of every adult in the United States. There's too many of them. A statistic is the corresponding number which describes a sample. So this sample mean, x bar, is the mean of whatever sample you have, standard deviation s, sample proportion p hat. So different symbols depending on whether you're talking about a population or a sample. And the whole game is to use the statistic, the sample value, to predict or answer questions about the parameter, about the population value. So we'll call the sampling distribution of a proportion. So in this screencast, we'll focus on one population proportion. Suppose you want to know the proportion of a population which is going to vote for your candidate, or the proportion of U.S. adults who smoke cigarettes, or the proportion of people in your company's market who have a favorable opinion of your product. The collection of all possible sample proportions, p hat, is called the sampling distribution, and it follows a normal distribution for large N with mean p, the population proportion, and standard deviation square root of p, 1 minus p over n. We've seen this already. So with confidence intervals, we use that sampling distribution to estimate the population. It's the normal distribution which makes the whole thing work. Recall that in any normal distribution, 95% of the individuals have z-scores between negative 1.96 and positive 1.96. We usually use just negative 2 to 2. Within 2 standard deviations of the mean is 95% of the individuals. And you can check that using Excel and the norm_dist function. And if we wanted 90%, we could apply it. For 90%, you should get 1.645 plus and minus. Okay, back to 95%. So the idea is that if 95% of the individuals have z-scores between negative 1.96 and positive 1.96, then there's a 95% chance that a random individual is within 1.96 standard deviations of the mean. That's what a z-score is. So if you have a random individual in any normal distribution, there's a 95% chance that the mean is within 1.96 standard deviations of that individual. So if you have one individual sample proportion, p hat, then there's a 95% chance that the actual proportion is within 1.96 standard deviations, but the standard deviation is this, square root of p, 1 minus p over n. So pick a random p hat. We can be pretty sure that the actual p, because that's the mean of the sampling distribution, the actual p is within this range of your p hat. Now, we don't know p, so we can't measure that standard deviation directly, but using p hat there is good enough. And so we conclude there's a 95% chance that the population proportion p is in this range. P hat plus or minus 1.96, square root of p hat 1 minus p hat over n. Confidence interval. More generally, the formula is p hat plus or minus z star, where z star corresponds to the level of confidence you want. So for 95%, 1.96. If you just needed 90%, it'd be that 1.645. And using norm_s inverse, you can find whatever z star needs to be. So let's look at an example. In a sample of 1,000 consumers, you find that 580 have a favorable view of your product, so p hat is 0.58, 580 divided by 1,000. So we calculate our estimate for the standard deviation. This is called the standard error, by the way, because it's estimating the standard deviation. multiply it by 1.96 for the z star, get 0.03, that's called the margin of error. So you have a 95% confidence interval for the proportion of consumers who view your product favorably is that 0.58 plus and minus 0.03, plus and minus your margin of error. So that's how we get a confidence interval for a proportion, and we'll be using Excel to do some of the hard work for us so we don't get caught up in calculations. Okay, so with confidence intervals we estimate a parameter of interest. With hypothesis testing we compare a parameter to a given value or test a hypothesis about it. So for example, is the proportion of cat lovers in Wisconsin more than 0.41? There's an important question. Everybody wants to know the answer to that. So there's our question, is p greater than 0.41? So we survey 1,000 randomly chosen Wisconsinites and find that 450 of them like cats a lot. This is a sample proportion, p hat of 0.45, 450 out of 1,000. Well, that's certainly more than 0.41, but maybe that's just random chance. Maybe you just happened to get a sample that was that big. So ask yourself this question. If p really is 0.41, how surprising would that 0.45 figure be? Would it be unusual to find 450 out of 1,000 if the actual population proportion is 0.41? And n is equal to 1,000, and then for sample proportions, the mean is 0.41 and the standard deviation is this 0.0156. So if the population proportion only is 0.41, then this 0.45 came out of a normal distribution with mean 0.41, standard deviation 0.0156. So we can ask what its z-score would be and how likely it is that it would be that high. So with norm-s-dist, we find that the probability of getting a sample proportion that high or higher is 1 minus, because it's greater than, norm-s-dist 2.56, which is 0.005. So if the proportion of cat lovers in Wisconsin really was 0.41 and wasn't higher, then the data we observed would have a less than 0.5% chance of occurring. It's possible, but it's really unlikely. So our survey results would have been very, very, very unlikely if the proportion was 0.41. So we say that our data was statistically significant, unlikely to be due to chance, and we conclude that the proportion of Wisconsinites who like cats is greater than 0.41. Phew, good news for cat lovers everywhere. That nothing going on is, and the alternative is p greater than 0.41. And then we answer a probability question. If the null were true, what's the probability of getting data as extreme, as large, in the direction of the alternative hypothesis as we observed? And when the answer to that question is small, we say that the data is statistically significant. We reject the null hypothesis and conclude that the alternative is correct. So there are three forms of the alternative: p greater than, p less than, p not equal. The null always goes with the equal sign. Always, always, always. Which is your alternative? Well, it depends upon your research question, on what you actually hypothesized to be true. It depends on that. Where did you start? For all three cases, you answer the question. If the null were true, then what's the probability of getting data as extreme in the direction of the alternative as we actually observed? And we do this by computing what's now called a z-statistic, p hat minus p naught over standard error. And once we have z, we use the normal distribution and compute the desired probability. How likely is it that we get an observed sample proportion if the null hypothesis is correct? This probability is called, a little confusingly, the capital P p-value. And we use the normal distribution. We look at this area, p is less than p naught is our alternative. This area, p greater than p naught is our alternative, and both tails combined. It's called a two-sided test. So don't get confused about all the p's here. P is the true population proportion. P naught is the one that's in the null hypothesis. p hat is the sample proportion, and the p-value is the probability. So we compute a p-value. If it's too small, we reject the null hypothesis. How small? Well, the conventional number is 0.05. Something that happens less than 5% of the time is rare enough that it's probably not due to chance. But really, it depends upon what's at stake and on the individual researcher. So here are the summaries, steps. State the null alternative, compute the z-statistic, find the p-value, make a decision to reject or not reject the null hypothesis, and then be sure to answer the original research question in clear English. So tips. The null hypothesis is always of the form p equals p naught when you're talking about one population proportion. Rejecting the null means you have evidence that it's false and that the alternative is true. Not rejecting the null only means you don't have evidence that it's false. We never say that the null is true. When the p-value is small, we reject the null hypothesis. And remember that your decision, your conclusion is based on probability, and you could be wrong. Statistics gives evidence, but not proof.